Welcome back. This is Machine Learning lecture number 4. Last time we talked about how to formulate maximum margin linear classification as an optimization problem. Today we're going to try to understand the solutions to that optimization problem and how to find those solutions. If you recall, our objective function for learning problem, the objective function is decomposed into two parts. One is the average loss, trying to agree with the observation. And the other part is regularization, where we're trying to understand and bias the solution towards the type of solution we are interested in this case, maximum margin linear separators. So more specifically, in case of support vector machine, our average loss is an average hinge loss of the linear predictor on those training examples. When the agreement here falls below value 1, agreement between the linear function and the provided label, when that falls below 1, we start incurring loss. And the average of those losses is what we are trying to minimize. On the other hand, we have a regularization term that minimizing that regularization term will try to push those margin boundaries further and further apart. And the balance between these two are controlled by the regularization parameter lambda. And we are going to initially try to understand how the nature of the solution varies as a function of that regularization parameter. So here's the picture that you've seen before. Here's the objective function for learning as before. And the margin boundaries, where the linear predictor takes value 1 or minus 1, are distance 1 over the norm of the parameter vector apart. So when we minimize the regularization term here, we are pushing the margin boundaries further and further apart. And as we do that, we start hitting the actual training examples. The boundary needs to orient itself, and we may start incurring losses. So as we change the regularization parameter, lambda, we change the balance between these two terms. The larger the value lambda is, the more we try to push the margin boundaries apart. The smaller it is, the more emphasis we put on minimizing the average loss on the training examples, so we are trying to classify the examples correctly within the margin boundaries, and the margin boundaries themselves will start shrinking towards the actual decision boundary. So let's see initially pictorially how this works. So here I have a set of training examples. This is a linearly separable problem, and I start with the regularization parameter being small, 0.1, so I'm emphasizing correct classification of these examples. And the solution that I get is then that all the examples are on the correct side of the decision boundary. For example, this one here is on the positive, on the correct side of the positive margin boundary. As I start increasing the value of lambda, I put more emphasis on the regularization term that is trying to push the margin boundaries further and further apart. In this case, they did not yet move because that additional emphasis on the regularization term is not enough to counterbalance losses that I would incur if I push the margin boundaries past the actual examples. As I increase the value of lambda further, I start allowing some of the margin boundaries to let the examples within the actual margin boundaries. As I increase that further, the solution changes. The solution to the optimization problem will be different. And as you can see, the further and further the margin boundaries are pushed, the more the solution will be guided by the bulk of the points rather than just the points that are right close to the decision boundary. So the solution changes as we change the regularization parameter. Here's another example where the problem is actually already not linearly separable, and I have a small value of the regularization parameter, but I cannot find a separable solution, so some of the margin constraints are violated, so I will incur losses on some of those points already here. As I start increasing the value of the regularization parameter lambda, the solution starts changing as before, being guided more by where the bulk of the points are, similarly to before. Let's now look at how changing the values of the regularization parameter lambda changes the training and test average losses or errors. As we emphasize the margin, we are less and less able to fit the training sample, so the losses would increase. As we decrease the value of lambda, we emphasize the training losses, and as a result, we would find solutions theta and theta naught where the training loss is smaller. Now we can understand this as a function of lambda, but I will actually plot it as a function of 1 over lambda. That's a little bit easier conceptually. So I will divide the objective function here with 1 over lambda. That doesn't change the optimizing values of theta and theta naught. I get lambda here, and this lambda goes away. And then I will just call this coefficient here c. So c is essentially 1 over lambda. So as c is large, we emphasize losses. As c is small, we emphasize simpler solutions that have a large margin. So as we now plot things along this axis, when c is small, we are looking for a simple solution. As c is large, we are looking for a complex solution that fits the training examples better. Now we can plot how the training loss behaves as a function of c. So for any value of c, I will solve for theta and theta naught, and then plot the corresponding average training loss. That curve would look something like this. Notice that it is monotonically decreasing the more I emphasize the training loss in the objective function, the lower the value will be. It may not go exactly to 0 because the problem may not be linearly separable, and as a result, I couldn't achieve a 0 average loss. So this curve here is now our training loss. Now we can imagine that for any value of c, we get the solution, and we can evaluate also the test loss or test error corresponding to that theta and theta naught. We cannot really do that, but we can imagine what the solution or what the value would be. That curve as a function of c would look something like this. It would have this stereotypical U-shaped form. First of all, it's typically higher than the training loss, since we are not fitting to those examples. And so this is now our test loss or test error, loosely speaking. So our vertical axis here is loss or error, and we are plotting them as a function of the value c that relates to our regularization parameter. Now there's a sweet spot here, an optimal value of c, call it c star, that would minimize the test loss or test error. So if we could find that value of this c and get the solution based on the training set, we would actually get the best generalizing method. We would actually be able to minimize the test loss. Now we cannot do that, but we will talk shortly about how to approximately do that. Let's look at this qualitatively though. This value of C star divides the problem into two regimes. In this regime, we are actually under fitting. In this regime, where C is larger than C star, we are overfitting. Now, the meaning of these terms is the following. If I'm underfitting, if I make the method more complex, i.e., I increase the value of C, I will actually improve my test performance. If I'm overfitting, then making the method even more complex will result in a poorer test loss or error. So I will do less well as a result. All right, so how do we get some value of C star? So we can simulate evaluating the test losses as follows. We will actually take here a box that I will now use as a representation of the full training set available to me. I will divide that into two pieces. One which is now the new training set, which is slightly smaller than before, and then the remaining portion that I will call validation set is now our pretend test set. So how we going to use this? We take that smaller training set, we find based on that set or those examples only the values of theta and theta naught by minimizing this objective function. Then we take the corresponding values of theta and theta naught and use the validation examples to evaluate an approximate test error. So instead, what we are evaluating here is not actually the test loss or test error. We are evaluating the validation loss or validation error. And then we find the value of C that actually optimizes the validation performance, optimizes the performance on those pretend test examples. So we don't get C star exactly, but we get some estimate, approximate value of C star. So far, we've seen how to qualitatively understand the type of solutions that we get when we vary the regularization parameter and optimize with respect to theta and theta naught. Now we are going to talk about actually algorithms for finding those solutions. So as a preface, let's talk very briefly about what gradient descent is. So I have here, for simplicity, just a scalar parameter theta, and some objective function with respect to that parameter. For example, something like this. So I have some starting parameter value theta, and I'm going to try to change the parameter value so as to get closer to the minimum of the function. At any point here, at the starting point, I can compute the slope of that function. That slope is given by the derivative of the objective function with respect to the parameter value, theta. If that slope is positive, if I move in the same direction, in the positive direction, I'm going to increase the function. If I move in the opposite direction of the sign of the slope, I will decrease the function. So my gradient descent update rule here is getting a new parameter value theta in terms of the old one and moving in the negative direction of the derivative or the gradient of the function. I'm going to also include here a step size or learning rate parameter. And the role of this is not to take too large of a step so that I would actually find myself somewhere where the value of the objective function might be the same or even larger. Okay? And if the function is nice, so there's a little convex curvature at every point, meaning that it's a strongly convex function, then there would be a constant learning rate small enough that I'm guaranteed quickly to get to the minimum of that function. Now, if I have a multidimensional case, so I have multiple parameters, theta 1, theta 2, and the function would look something like this now, and I'm trying to get to the minimum of that bowl-shaped function, then all I do is to move each of the parameters exactly as we did before when the function was only a function at a single scalar. So with respect to each of the parameters, I'm going to move it in the negative direction of the derivative of the function with respect to that particular parameter. Okay, I can write this also in a vector form. So for all the coordinates of theta as a vector, now I'm updating by taking the old vector and moving in the negative direction of now the gradient of the function with respect to the parameters. And this gradient is nothing but a concatenation of these individual derivatives with respect to the parameters. So derivative of the function with respect to the first coordinate, and then derivative of the function with respect to the last coordinate, call it theta d, if there are d coordinates in theta. Now, our problem looks like this. We have an average of the training losses plus regularization term. And we can write it by moving the regularization term inside the average, since it doesn't depend on the training example, so any average over that would return the same thing. I'm also going to simplify our calculations by omitting the offset parameter completely here. So one way to understand this is that we actually have now an average of simpler objective functions. So we have a sum over the training examples here with respect to the simpler example-specific objective functions that involve a simple loss function plus the regularization term. Okay. Now, one way to understand this is that the objective function is actually an average and expectation over these individual terms. So we should be able to update the parameters stochastically by taking each individual term individually, sampled at random. So sample a training example at random, look at each individual objective function, and nudge the parameters in the direction that optimizes that particular term. And since we are resampling another training example, nudging the parameters in slightly different direction and so on, if we take small steps like that, then on average, we're going to move in the direction that optimizes what we want. Why do we do this rather than a full gradient descent step with respect to the whole objective function? The reason is that it is actually a more efficient way to do the optimization. So what we do is we sample a training example I at random from the set of possible indices of the training samples. And then we perform a gradient descent update with respect to the selected sampled term. So we move parameters in the direction that seems to optimize that particular term in the objective function. Okay. Now, since we are doing this stochastically, we introduce some randomness here. We actually need to decrease the learning rate parameter in order to make this converge. So what we actually need to do is to have the learning rate go to 0 as a function of the iterations of this update. More precisely, we want it to sum the learning rate sum to infinity. If we sum over all the iterations, what that means is that we retain enough steam to be able to nudge the parameters wherever we are towards the minimum. But then, on the other hand, we need to reduce the variance from the stochasticity that we're introducing. So we have the parameters be something called square summable, meaning that the squared values of those parameters are actually finite. So for example, eta t equals 1 over 1 plus t would suffice to satisfy these constraints. Now let's look at how we actually compute the gradient. Here we have now the objective function without the offset parameter, and we have the j ith term here and the average of those. So our update here is then to sample I at random, and now take a parameter update, the old parameter value, nudge it in the direction of the gradient with respect to the parameters of now the hinge loss of that particular training example with respect to the parameters theta plus the regularization term. So let's see what that gradient actually amounts to. So now we need to take the gradient with respect to the parameters of both terms here. And what we get is here, the loss derivative of the loss. We can divide it into two parts. When the loss is 0, then the gradient is also 0 as a vector here. So when the loss is 0, then nothing will come out of that gradient. When the loss is non-zero, then the hinge loss is actually 1 minus its argument. The argument is just a linear function of theta. When you take a gradient of such thing with respect to the parameters, you get just the multiplying terms here. So you will get here minus from that 1 minus part, and then label, which is a scalar, times xi, which is a vector. So this is the gradient of the hinge loss when the loss is non-zero. And then we have another term here coming from the regularization term. That will be, the gradient of that will be just lambda times the parameter value itself. All right, so there are three differences between this and our earlier perceptron algorithm. First is that we are actually using a decreasing learning rate due to the stochasticity. The second difference is that we are actually performing the update even if we are correctly classifying the example, because the regularization term will always yield an update regardless of what the loss is. And the role of that regularization term is to nudge the parameters a little bit backwards, so decrease the norm of the parameter vector at every step, which corresponds to trying to maximize the margin. To counterbalance that, we will get a non-zero derivative from the loss terms if the loss is non-zero. And that update looks like the perceptron update, but it is actually made even if we correctly classify the example. If the example is within the margin boundaries, you would get a non-zero loss. So here we have just a better way of writing what that stochastic gradient descent update, or SGD update, looks like. We can also solve the problem by actually solving the optimization problem. So for example, if we take the simple case where we don't allow any errors, the problem is linearly separable and we don't allow any errors. So if we want all the training examples to have zero hinge loss, they would have to have the agreement greater or equal to 1. And subject to those constraints, we're trying to minimize the norm of the parameter vector, maximize the margin, subject to having the examples on the correct sides of the margin boundaries. What we get here is now a quadratic program that there are packages for trying to solve. And you can also generalize this to allowing these constraints to be violated and incorporating the actual loss value. It would be a slightly modified version of the quadratic programming problem. The solution for this strict case is that you always have some subset of points that are exactly on the margin boundary, because we increase the margin until we cannot do it anymore and we start hitting the training examples. But we cannot go further because in this simple case, we strictly try to enforce the margin constraints. What we have seen so far is how to understand the optimization problem corresponding to maximum margin linear classification, the effect of regularization as we change the regularization parameter, how the solution changes qualitatively, as well as in terms of generalization. We also saw how to actually solve the associated optimization problem using gradient descent updates, in particular stochastic gradient descent updates that are efficient to perform for such functions. We also briefly discussed how to turn the associated optimization problem into a quadratic programming problem and maybe use existing packages that are available for solving it.